We're very familiar with the concept of an average. You find the average of your grade, you find your average speed, but let's consider average rate of change across a broader spectrum. Let's start with a situation we know and consider we are covering 200 miles in 4 hours. We can recognize that to find our rate of change or our average speed, we're going to do distance divided by time. Now, since we are traveling a distance of 200 miles in 4 hours, that's our time, we can very easily calculate that our average rate of change is 50 miles per hour. If you look at this graphically, we can plot T can be our x-axis and D can be our y-axis, and you can see that we can plot this linearly. Again, note that the average rate of change there is change in distance over change in time, which in this case can be thought of as the function at x2, whatever that time is, minus the function at x1 over the change in time. So in this case, the distance when x is 4 hours is a distance of 200. Our starting distance was 0, and our time was 4 minus 0 for, again, an average speed of 50 miles per hour. Note, this is the slope of this line. However, what do we do if the function we're looking at is not linear? Well, let's consider the function 2 over x. If we want to write an expression for the average rate of change, between two x's, and we'll call them x and x plus h, we know that the average rate is the change in y over the change in x. Given our two x's, we're going to find the value of the function at x plus 8 minus the value of the function at x divided by the change in the x values, which is simply going to be x plus h minus x, which results in just h. Plugging in the value of the function, we get 2 over x plus h minus 2 over x. Now here we're dealing with a complex fraction, so remembering your rules there, we can think of this as 2 over x plus h minus 2 over x divided by h. And when we divide fractions, we are going to multiply by the reciprocal. So this can be thought of as that difference multiplied by 1 over h. And so multiplying through, we get 2 over h times x plus h minus 2 over xh. And because we're dealing with fractions, we have to find the least common denominator, which in this case is going to be x plus h. To get the denominators to match, in this case, we're missing an x, so we're going to multiply top and bottom by x. In this case, we're missing the x plus h term, so we multiply top and bottom by that. This results in 2x minus 2 times x plus h all over xh times x plus h. When we distribute, we get 2x minus 2x minus 2h over x times h times x plus h. Notice these cancel, and our average rate of change is going to be negative 2h over xh times x plus h. But again, we can still factor out that h, and so we can further simplify and get our average rate of change is going to be negative 2 over x times x plus h. And again, this is an average rate of change because we took the change in the y values divided by the change in the x values. Let's look at an example that maybe seem a little more practical. Consider we have a ball that's dropped from a high distance, and we can describe the distance the ball has fallen by the function d equals 16t squared. I've created a table here to show you the distance the ball falls in the first 5 seconds. We're going to use this table to look a little bit at the average rate of change. To figure out how far the ball falls in the first 3 seconds, notice at time 0, the ball has fallen 0 distance. However, in 3 seconds, the distance can be calculated by d equals 16 times 3 squared, which results in 144. If we wanted to find the average velocity in the first 3 seconds, remember that's going to be the change in y over the change in x, which in this case is the change in distance over the change in time. We just calculated a change in distance of 144, I believe feet is what we're working in, yes, divided by 3 seconds. And when I divide those two, I get 48 feet per second. A more important question that we may be wishing to ask is, how fast is it traveling at exactly 3 seconds? Clearly, it's falling a little bit further each time. You can notice your change in distance, your delta D is getting bigger after every second. So what if we wanted to know exactly how fast it's traveling at 3 seconds? Well, the short answer is at this point, we don't know, but in our next section, we're going to create some tools that allow us to figure out instantaneous rate of change versus average rate of change.